Welcome to our final video in the Sequences and Series unit. Here we'll look at geometric sequences and series. So what does geometric mean? Well, let's start with what it doesn't mean. It doesn't have anything whatsoever to do with geometry, at least not as we know it today. So what does it mean? Well, it refers to a sequence or series that is somehow multiplication related, also known as increasing or decreasing exponentially. I'll show you some examples. The phrase geometric can apply to a sequence or a series. Here's a sequence that's geometric. I'm going to pause while you try to detect the pattern. If your brain went instantly to addition, like we're adding 6 or adding 12, that's not the case. Notice what's happening here is that the terms are doubling. In other words, they're increasing by a factor of 2. 6 times 2 is 12, 12 times 2 is 24, 24 times 2 is 48, and so on. Another way to say that is that the sequence has a common ratio of 2. They call it a common ratio because the ratio of any term to its previous will always be 2. 12 divided by 6 is 2, 24 divided by 12 is 2, and so on. And while ratio does imply division, and that is the reason for the name, you're better off thinking of the common ratio as the number we're multiplying each term by to get to the next term. And we're clearly multiplying by 2 term to term in the sequence. By the way, the letter R represents the common ratio in geometric sequences and series. So we would say that R equals 2 for this sequence. Here's a series. Now notice it's a bunch of numbers added together, but there's an actual pattern to those numbers. It's hard to see, but I will pause while you try to detect the pattern. That's very challenging to see for the average student, but it does turn out that each term can be multiplied by the number 1/3 to get the negative 1/3, to get the next term. So we would say that the terms in this series are changing by a factor of negative 2/3. That's just a fancy way of saying, negative 1/3. That's just a fancy way of saying negative 1/3 times any term in the sequence equals the next term. By the way, you might want to think of this as a division instead. Watch along in the series as I describe. Think of this as being a series where we divide each term by negative 3 to get the next one. 54 divided by negative 3 is negative 18. Negative 18 divided by negative 3 is positive 6. Positive 6 divided by negative 3 is negative 2. If you need to pause the video now to convince yourself that we're multiplying each term by negative 1/3, in other words, dividing by negative 3 to get the next term, now would be a good time to pause. We could also say that the common ratio is negative 1/3, or that R is negative 1/3. Here's another sequence. I'll pause while you try to identify the pattern. You may have noticed that each term is half the size of the previous. Another way to say that is we're decreasing by a factor of 2, the same as cutting in half, or that the common ratio is a half, or that R is a half. And here's one more series. See if you can notice the pattern. What's happening in this series, in plain English, the terms are tripling as we go from one to the next. Said more mathematically, the terms are increasing by a factor of 3, or that the common ratio is 3, or that r is 3, all of which mean the same thing. Let's look at our first example. Here's a sequence. Suppose we were being asked to find the general term. Well, if this sequence turns out to be a geometric sequence, then we can use this generic formula to find the general term. The first thing I'd like to do is confirm that the sequence is geometric. So we'll ask the question, is it? Well, for a sequence to be geometric, that would mean that any term multiplied by the same constant multiplier, called r, would equal the next term. Of course, that begs the question, if this were to be geometric, wouldn't that mean 16 times some number equals 12? Well, is that possible? 16 times some number equal to 12? Just for algebraic simplicity, call that number r. How can we figure out what value of r times 16 would equal 12? Well, using basic algebra, of course, and dividing both sides by 16. And when we reduce that fraction, we get 3/4. Now, that doesn't prove that the sequence is geometric, but it does tell us that the first term times 3/4 would equal the second term. To confirm that this entire sequence actually is geometric, we'd have to continue showing that that pattern, that 12 times 3/4 equals 9. Well, that turns out to be true, and if you'd like to pause the video for each one of these and check the fraction algebra, you can. That does in fact work out to be 9. But again, to continue to be geometric, 9 times 3/4 would have to be the next term. Well, it turns out that that's true as well. And likewise, 27/4 times 3/4 does work out to be the next term. And so all of that confirms that we have a geometric sequence. And the answer to this question is yes. Well, now that we know that we have a geometric sequence, then it's okay to use this formula to find the general term. So I'm going to take that formula and use it. Now you'll recall that finding a general term does not involve plugging in any specific number for n, since it is a general term after all, and therefore I'm going to leave the n's as the letter n. Good enough. But what I can do is plug in the a1 or first term value and the r value associated with this sequence. But of course, a1 is 16, and r, we discovered, was 3/4. So I can plug those two values in to my general term equation. Now, as far as algebraic simplification goes, that's about all we can do, and we usually stop right at this stage with our general term rather than trying to simplify any further. So there it is, the general term, done with this question. As an afterthought, though, just to remind ourselves what a general term actually means, let's go beyond the problem. What if they asked you for the fifth term of this sequence? Wouldn't we get that by plugging 5 in for n? Let's do that. Plugging 5 in for n, ultimately, if you do all the algebra, and I don't want to turn this into a fraction lesson, so I won't, but if you do all the algebra on this, 16 goes into 256 16 times, as it turns out, and what we find is that the fifth term of this sequence is 81/16. By the way, we already knew that the fifth term was 81/16. I just wanted to take the opportunity to show you what the general term is. As a reminder, the general term is that formula that will allow you to find any term. Let's look at another example. This time we'll look at a geometric series. Suppose we were asked to find the sum of the first 10 terms. In other words, add up the first 10 terms of this series. This formula, as it turns out, is something that we can use for a finite sum of a geometric series. When I say finite, I mean not infinite, And since we're being asked to find only the sum of the first 10 terms, that's clearly finite. But this formula is only valid if the series that we have is geometric. So the question is the series geometric? Well, look up at the top of the screen and you'll notice the terms, in some sense, are doubling from one to the next. In fact, if you look more specifically, you'll notice that each term multiplied by -2 equals the next term. Notice, 5 times -2 is -10. That times -2 is +20. That times -2 is -40, and so on. This, by the way, is called an alternating series because the signs alternate between positive and negative. And you get an alternating series whenever your common ratio, or R value, is a negative number. But to the question, is this series geometric? The answer is yes. And because it is, I'm okay to use the finite sum formula for geometric series. So I'm going to take that formula. And remember, we're being asked to find the sum of the first 10 terms. So I'm going to replace n with 10. Now, in order to complete the sum of the first 10 terms, I need to know A1 and R from my series. But of course, I've discovered what R is, and I know what A1 is. Therefore, I can plug those values in. And once you've done that, all that's left to do is the arithmetic. -2 to the 10th power. Work out the numerator and denominator. Divide and multiply. And we've just found the sum of the first 10 terms of this series. Now I'm done with the problem, but it's worth noting you probably could have done this without the formula. All you would have had to do is literally write out the first 10 terms of the series, which I've done here, and then worked it out. Another way around the formula if you so choose. Next, I'd like to examine infinite geometric series, meaning the adding of an infinite number of terms or numbers. Before I get to the problem that I'm going to showcase here, I'd like to bring back something from video 2. In video 2, we saw this infinite series. Notice the 3 dots at the end. The ellipsis indicates that this pattern continues forever and that we're adding an infinite number of numbers in some sense. And I'd like to remind you what that means before we do the actual mechanics of this. So first of all, notice that in each case here, these terms are half the size of the previous as we go through this. We didn't have this vocabulary at the time when we saw this in video 2, but we would now say that this is a geometric series with an R value of a half, meaning any term multiplied by a half would give us the next term. Now we discussed that this series had a value of 12. And the question is, how can an infinite number of numbers add up to 12? Well, this is the idea. So I expanded the series and wrote out more terms than were originally visible. And we went through the following thought process. First 2 terms add up to 9. The first 3 terms add up to 10.5. We call these partial sums. The fourth partial sum adds up to 11.25. And if I continue to look at partial sums, going further and further out into the series, what I discover, I'll stop here, what I discover is that the partial sums get closer and closer and closer to 12. Now, for that reason, because the partial sums never exceed 12, but get infinitely close to 12, or as close to 12 as I'd like, we say that this infinite series has a value of 12. Now, just to be clear, this is the concept. not the procedure necessarily. If you wanted to know the infinite sum, you wouldn't necessarily take larger and larger partial sums and see what the results were getting closer to. That's just something I mentioned to give you a sense of what it means that this thing has a sum of 12. But it's not procedurally a very good idea to keep taking more extensive partial sums. So to look at what a good mathematical idea and formula would be in this case, let's look at this geometric series. Now, if we have an infinite sum, it turns out, and we do here because of the dot, dot, dot at the end, it turns out that we can use this as my infinite sum formula. But before we can use this, we have to ask ourselves two questions. First, is the series geometric? Because if it isn't, then this formula is useless and meaningless. Well, it does appear, look at the top of your screen and you'll notice that it does appear that we have a geometric series here. In fact, wouldn't you agree that each term in the series is 1/3 of the size of the previous term? So we can say that we have a geometric series with an R value of 1/3 here. The answer to that question is yes. But furthermore, in order to be able to use this formula, it has to be true that R is between -1 and 1. Is the particular R value here between -1 and 1? Well, of course, the number 1/3 is between -1 and 1, and that's essentially the same as this stipulation here. That just says R has to be between -1 and 1. And the answer to that question is yes as well. And so, because the answer to both of these questions is yes, then it's okay to use this as my infinite sum formula. So I'm going to use that formula in this particular case. Well, to use this formula, I need to have numerical values for A1 and R. But of course, we know what A1 and the value of R are, and so I can plug those in to my infinite sum formula. At this point, the only thing left to do is the arithmetic. 1 minus 1/3 is 2/3. Using the reciprocal rule for division and doing a little arithmetic in my head tells us that this infinite sum is 27. And while I have the answer to the problem, I'd like to delve a little further into what that actually means. So to illustrate what it means, I decided to do the 10th partial sum. In other words, I decided to add up the first 10 terms of this geometric series. No reason I chose 10 other than just to make a point here of what interesting thing would happen when I do that. Now, in order to add up the first 10 terms of the geometric series, you have two choices. You can use the sum of the first n terms formula from last time, substituting 10 for n, that was from the last problem, or you could literally write out the first 10 terms and add them up. And I did that. Either one would have worked. I got a common denominator. It was quite a messy endeavor. I ultimately got this fraction. Okay, so that's the sum of the first 10 terms. But then I got a calculator and turned that fraction into a decimal. And I got something incredibly close to 27. And that's sort of the concept of what we mean when we say an infinite sum is 27. It means that the partial sums, as we go further out, here I've went 10 terms out, the partial sums get closer and closer to 27. Now, how is it possible that if only 10 terms of this series add up to about 26.999, then how could adding, say, 1 billion terms never exceed 27? We're so close to 27 after just the first 10 terms. Well, the reason is, as you go through the series, the terms get smaller and smaller and smaller and very much smaller, so much so that adding on 1 billion more terms, just to use billion as an example, Adding on a billion more terms still wouldn't get me over 27. It would just get me closer. And that concludes this 4-video series on sequences and series. Thank you for watching.